Welcome back, everyone. This is Professor Herring. Glad to have you here. In this video, we're going to continue our discussion about gases. Specifically, we're going to learn about the ideal gas law. So let's begin. We talked about in a previous video how you can relate the pressure to volume using Boyle's law, you can relate the volume to temperature using Charles' law, and you can relate the moles to volume using Avogadro's law. Well, if you take those relationships, which are illustrated here in the second column, and then combine them all together, we get a single relationship, and that is what we call the ideal gas law. Now, each of these relationships between volume and pressure, or volume and temperature, volume and moles, they have some constant. And really, we should call these K1, K2, and K3 because they're not the same constant. When we combine all three of these equations together, we also combine all three of the constants, K1 times K2 times K3, and that becomes what we now call R, which is the ideal gas law constant. And we can now use these relationships to describe any state for gases, for ideal gases rather. Oops, excuse me. For ideal gases. Let's just rewrite this. And the assumption here is about what an ideal gas is. And ideal gases, as we talked about with the kinetic molecular theory, we've said that gases do not occupy space. The particles themselves don't occupy space while they do fill their container, and that there's no intermolecular forces. We're going to learn in a little bit about exceptions to that and cases under which those assumptions fail. But for now, we're going to assume that the gas particles themselves occupy no volume relative to their container, and that there's no attraction or repulsion between those particles. And that allows us to use the ideal gas law. We also need to discuss what's called standard state conditions. And we define standard state as the temperature and pressure for gas particles. This is where the temperature is 0 degrees Celsius. You should also recognize that this is 273.15 degrees Kelvin and 1 atmosphere. We're going to talk about standard state conditions later when we're discussing enthalpy, and we'll see that the temperature is different. But for now, when we talk about STP, that's standard temperature and pressure. This is standard state for gases. And you need to remember that we're talking about 0 degrees Celsius and 1 atmosphere. You can think of this as essentially we're talking about water freezing. That's a benchmark that you could use. So let's combine all this together to solve a problem here. We have a balloon filled with helium and at a volume of 1 liter, 1.5 atmospheres, and 5 degrees Celsius. What's the volume of the balloon after half of the helium atoms leak out, the temperature raises to 10 degrees Celsius, and the pressure is reduced to 0.75 atmospheres? Well, there's a variety of ways that you could actually go about approaching this, but they all are going to rely on this relationship with the ideal gas law. And so what we need to recognize is that this describes a state. So in other words, if you're given the pressure and the volume and the moles, you could solve for the temperature. However, when you're changing states, you need to combine and rearrange the ideal gas law. So because the ideal gas constant R is a constant, we can set up two sets of relationships. One for our initial states and one for our final states. And we're given information. This is an initial volume, this is an initial pressure, this is an initial temperature. We're told information about a final number of molecules, a final temperature, and a final pressure. And so we know in the beginning all of these variables, except for we're trying to solve for the final volume of the balloon. So because these are both equal to R, we can set them equal to each other. Then, because we're solving for the final volume, we can rearrange these two equations to solve for volume and the final conditions, and then plug in our values. Now, when we do this, we know we have a starting pressure of 1.5 atmospheres, starting volume of 1 liter. But what about the moles? We're not actually explicitly told the number of moles of each. And so what we do know, though, is that the final moles is 1/2 of the initial moles. And so we can set that relationship. We know the initial temperature, or excuse me, the final temperature, the initial moles, the initial temperature, and the final pressure. And so what we see then is because there's a proportion in the number of moles, those moles are going to cancel out. The units of atmospheres will cancel out, and the units of Kelvin will cancel out. And that's going to get us our final volume of approximately 1 liter. And that's the case, it will be 1.0 liters when we account for significant figures. So it turns out that even with manipulating the different variables, because we manipulated them essentially equally in opposite directions, we didn't end up changing our final volume. Another word here, and when solving problems like these, what you could have done is you could have solved for the initial moles. And then you would have a specific value to plug in for N2. And that's fine as well. I show you this way to demonstrate that you can rearrange the equation algebraically first before plugging in your values. So now, why don't you try a problem? Determine what volume is occupied by 1 mole of gas at STP. Pause the video now and try this on your own. Welcome back. So in order to find the volume, we have to first rearrange our equation to solve for the volume. We know that we have 1 mole of gas, but what about our temperature and our pressure? And which R value do we use? This table is from the ebook, and you can see that there's different units. They all are per mole Kelvin, but they have different units in the numerator. And and when we use them just depends on the scenario, the context. Because we know that at STP we have 1 atmosphere and the temperature is 0 degrees Celsius, we know that we're going to use something involving atmospheres. So it makes most sense to use this value here. The temperature is 273.15 degrees Kelvin, and the pressure is 1 atmosphere. When you solve for that, you get 22.4 liters. And any gas is going to have a molar volume, any ideal gas at STP will have this volume. Notice that we didn't specify if we were talking about helium or hydrogen or nitrogen. As long as it's an ideal gas at STP, it will occupy this volume. Let's now talk about density. So we know that density is defined as the mass per unit volume. We can write that as m over v. We also know that we can express mass in terms of moles and the molarity. And so if we multiply moles times the molarity, that's going to equal the mass. By combining these two relationships and rearranging and solving, we can then substitute that into the ideal gas law because we have common factors of moles and volume. When we rearrange and solve for moles over volume, we get moles over volume equals the pressure over the gas constant and the temperature. We can then substitute in this relationship with density and get that the density is equal to pressure times the molar mass over the gas constant and the temperature. We could also rearrange and solve for the molar mass using the density. And it turns out that this method was used historically for long periods of time, and you could still use it today. You can, by measuring the density of a gas, you can identify what it is. That's illustrated here on this slide, where what you do is you take a flask where you evacuate it using a high-powered vacuum, laboratory vacuum that is, not the kind that you're going to use to clean your floors. Pull out all of the air, and then weigh the flask. You can tear the flask or you can get its weight. And then by inserting your gas and weighing how much the gas weighs, you can then determine the density. Because you know the mass of the gas and you know the volume of the flask, you can then find the density. Then, using the relationship that we described already, molar mass equals density times RT over P. If you know the temperature and you know the pressure, we can then find the molar mass, which allows us to identify the gas. So here's a conceptual question. Pause the video now and think about what would decrease the density of the gas, either increasing its temperature or increasing the pressure. Hopefully you've taken a moment to think about it. Well, which is it? Let's look at this relationship. Again, density is the molar mass times the pressure over R times the temperature. If we increase the temperature, the denominator increases and the numerator stays the same. What's going to happen to our density? The density is going to have to go down. And so what does increasing the pressure do? Increasing the pressure is going to lead to it's a direct relationship with density, so an increase in pressure leads to an increase in density. So just to clarify, increasing the pressure is going to increase the density. And that makes sense if you think about what we're doing is we're compacting those particles together with an increased pressure, so we're decreasing the space between them, increasing the density. However, if we increase the temperature, our density will go down, and that makes sense because you're giving them more energy, they're spreading out. They're increasing their volume and therefore becoming less dense. Why don't you try this calculation problem now? Pause the video and try this before moving on. Welcome back. So we want to know what's the density of helium gas under a given set of conditions. So we have this relationship describing the density as related to the molar mass, pressure, and temperature. We are going to use this R constant, and we also need to convert torus into atmospheres. So because we're using helium gas, we would need to look up its molar mass. On the periodic table, you see that it's approximately 4 grams per mole. The temperature of our system is 21 plus 273.15. That gets us 294.15 degrees Kelvin. And our pressure, when converting from torr to atmospheres, is just under 1 atmosphere. We plug all of these values into our relationship, the molar mass, pressure, R value, and the temperature, and we get a density of approximately 0.16 grams per liter. That gives us our answer choice of B. The next 2 slides are just going to be some extra practice problems. So if you feel like you're good, you can finish watching. You can finish right now, or you can hang on and we'll solve a couple more problems together. So this plot shows the distribution of speeds of different gases at the same temperature. We want to know if they're all in if each one is in a 1 liter box at STP, which one's going to have the greatest density? Take a moment to think through this on your own, and then I'll walk you through a solution. Welcome back. So, density. Density is proportional to the molar mass. We know that the most dense gas is going to have the largest molar mass. And we also know that the RMS speed is related to the molar mass, but it's inversely related. So a high molar mass leads to a low RMS speed, and therefore the curves, the Boltzmann distribution curves with the lowest RMS speed, which is A, is going to have the highest molar mass. E, which has the highest RMS speed, is going to have the lowest molar mass. And since we're looking for the one with the greatest density, we want the one with the highest molar mass, and that's going to be A. If we were to rank them by their density, we would see that E is the lowest density, followed by D, C, B, and then A. Again, the idea here is that we're relating the observed RMS speeds, the average speed of the collection of gas particles, to the molar mass, and then comparing the molar masses to determine the relative densities. Let's try one more problem. So if we have an equal mass of each gas put into a separate balloon, which will have the greatest volume? Assume they're at the same temperature and pressure. How do we think about this? Well, we know from the ideal gas law that there's a relationship between all of these different variables. We're assuming that there's the same temperature and pressure. So then we can essentially just relate moles to volume, and this is some constant we'll just call K. And so a higher moles means a higher volume. Well, since we have, and that's summarized here, we know that the number of moles is related to the mass and the molar mass. We know that each gas sample has the same mass, and therefore the sample with the larger molar mass is going to have the fewest number of moles. And if you wanted to try this out, we could plug in a value. Let's take helium. And let's just assume that we've got 20 grams of each. The moles of helium is going to be equal to 20 grams of helium over the molar mass. That's going to be equal to 5 moles. If we looked at the moles of hydrogen, that's going to be 20 grams of hydrogen over 2 grams per mole, and that's equal to 10 moles. And again, because they're at the same temperature and pressure, the higher number of moles leads to the higher volume. That's it for this video. Thanks for watching. If you have questions, ask on Piazza, in office hours, or recitation. Have a good day.